understand what's happening. It's just too bad. I can't understand it. I'll never be able to pass this. It's terrible. Oh, what am I going to do? Alright, so this video is about the major lab for weeks 5 and 6, and I'll work my way through it very quickly. I'm thinking that probably if I just worked by myself and did this type of circuit, it would take me about 5 or 6 minutes to go through. We might have a couple of small just inquiry type things during it, but I won't go as slowly as I've gone in the review of today's quiz. I'll go through a lot quicker than that. So the first thing that I do when I look at a circuit like this is to loop like values. I haven't left a resistor out of there, have I? There's no resistor on the bottom? Nothing?
Yes, there is.
There is?
Yes.
Dear, dear, dear.
150 ohms.
I thought there was a resistor there, my bad.
R5.
Yeah, because I know what would happen. I'll get halfway through solving this and someone will say, "Sir, you've forgotten the resistor." R5, how many ohms?
150.
150. Yeah, I thought there was another resistor there because I got the pen and I went to put a big loop around the two resistors and hang on, there's something not quite right. So I look at a circuit like this and I say to myself, I can see two resistors in series, so I do a loop around those. I can see a couple of resistors here in parallel, so I'll do a loop around those. And then before I do anything else, I'm going to go ahead and solve these. 330 plus 150, they are the right values, aren't they?
480.
R4? It is 330?
Yes, 330.
330 and 150,
Yep.
So 480 ohms. Oh, okay. I just seem to recall that I looked at it before, it was 500, my bad. 480 ohms. So that was just R4 plus R5, and then I'll go to the blue pen. 680 and 560, so 680 times 560 divided by, what's that, 1180, 1240, is it? Is that correct?
What, which one? R2, R3?
1240 on the bottom?
I didn't do it like that, but yeah. I trust you. I hope.
Yeah. 680 times 560 divided by 1240.
Should be 307.
Like product over sum, usually it's only convenient to use if you can add up the bottom line in your head, you know. 307. I'm not worried about the 0.1. 307 ohms. And then, because that 307 is in series with, it's in series with the 480, I have to add those together. Jeez. $787 ohms. Now that's 787 ohms. Would have liked another colour. Look, I don't know how well the green pen will come out.
Bring it light.
Yeah, I've done all that. I
I'm normally really reluctant to use green because green just does not work well at all with the video. So I'm doing a loop now around the whole lot. I already know that the sum of the blue loop and the red loop is 787 ohms, so the parallel and the series, and then they are all in series together. But the blue loop and the red loop, which are in series, are in parallel with R6. So that'll be 787 in parallel with 1000 ohms. because I've got 1000 ohms there, 787 ohms there.
Yes, not so far.
So 1 on 787 plus 1 on 1000, and we'll call this the green loop.
So could you use product of a sum for that?
Yeah, of course you could. You could use product over sum.
You don't usually roll like that.
So 787 function 1 on x, add 1 naught 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 function 1 on x equals function 1 on x, 440 ohms. And if green was better for the projector, I would have, for the camera, I would have done that equation in green. So I'll just put here in green 440 ohms, and I'll just sort of hope that you can sort of see it a bit, but I'm probably being very wishful. 440 ohms is all of that, and then can you see that R1, the current has to come in through here, from the battery, in here, come down through here, keep coming, and go back up and back up into the battery. So therefore, 270 plus 440 plus 330, this will be RT. This will be what the battery is seeing. RT is what the battery is seeing. Looking into here, it's a pretty crappy eye, but looking into the circuit, it's seeing this sum here. So 270 plus 440 plus 330. 1040 ohms. 1040 ohms. And that's what you got before, wasn't it? We talked about that before lunch. 1040 ohms. Okay. So then I total, it's nice and black, I total equals V supply. I'll call this from time to time V total, and from other time to time I'll call it V supply, VS, divided by R total. So it'll be 15 divided by that, so it'll be 1 on that times 15 is 14.42 milliamps.
Mine's just different to yours, to a 0.02 difference.
Don't worry too much about that. 14.42 milliamps IT. Right, so that 14.42 milliamps comes into this node here. This colour situation is getting pretty grim. Node. 14.42 comes into the node, and then out of that node I've got current coming down here, and I've got current going there, and I've got current going there. Well, because I combined those two resistors and made one new resistance called 787 for those two loops, I end up with a new circuit. And I think at this stage we probably should draw a new circuit. Quickly sketch one up. Here's the battery, top resistance down through there, bottom resistance, yeah, back up to the battery, and then another resistance over there and down there. So what we're saying here as far as the current goes, we're at this node, and I've got 14.42 milliamps coming in here and going through that resistor into that node, and then it splits, and I've got some current going down there and I've got some current going down through there. And this one here is 787 ohms, and this one here is 1000 ohms. And the REQ of both of those is 440 ohms. That's the REQ for both of those. So using our current divider, and we need the REQ over Rx times I node. So therefore that'll break down to 440, case 1,
Over 1,000.
case 1, and case 2. Case 1, the 440 divided by 1000 times 14.42, and I'm just going to leave it in whole value as 14.42 because the answer will be in milliamps. And case 2 will be 440 divided by 787 times 14.42. Equals, magically do those, 440 divided by 1,000 times 14.42, 14.42 equals 6.35. I'll round it. 6.34.
Yeah, I got that right, mate.
6.34 milliamps, and then 440 divided by 787 times 14.42 equals 8.06.
Which answer for that one, sir?
Say again?
What 8.06 milliamps towards which line?
That's case 2, 787.
The
787.
combination of R2 and R4.
When we apply these values, because I've simplified the circuit to show the two current branches, and that 787 is all of this together, now I'll put that new 8.06 up here. That's 8.06 milliamps flowing through the two of those and down there. So, aha! We probably need another current divider because I just worked with one big 787 ohm resistor. That's fine to get the currents through these, 8.06, but now what about the currents through those? Ooh, we need a new case 1, case 2, because I've got 680 ohm, 560 ohm, 8.06 comes out, so therefore 8.06 must be going in, and when I say going in, I'm talking about here's my node, which is this node here, and into that node we had 14.42. But then out of that node, one wire, and then splitting into two resistors, and then they join up again to continue going. And we had other current coming down here. It's at this point here that I've got that 8.06. 8.06, and of course I must have 8.06 coming in. Current going straight through. So I have to split that now between R2 and R3. Now we can do it. I'll bring the board across a little bit and I'll just redraw that part of the circuit and then we'll solve that. So 680 and 560, what was the REQ for that? We worked that out before. That was, no, 307, wasn't it? Agreed? Blue loop, 307. R2, R3, 680, 560, REQ, 330. Don't want to make a mistake here. I beg your pardon, 307.
Yeah.
307 ohms. Current divider. It'd be REQ over the resistor you want to find, Rx times I node. I node is going to be the 8.06 milliamps. $307 divided by 680 And that's case 1. Case 2, 307 over 560 times 8.06 milliamps equals, oh, it's getting repetitive, isn't it? 307 on 680. 307 divided by 680 times 8.06 equals 3.64.
Oh, that's far from right. So why times by 8.06 milliamps?
Still on the board
That's
there.
not the
Yeah, the I not there
That's
is
for
14.42, sir.
How does that?
No,
I times it by
No, no, no.
14.4.
no. 14.42 here, but that 14.42 has split. There is 6.34 coming down here, 6.34, and there's 8.06 going that way. Add them up. 6.34 plus 8.06 adds to 14.42.
So you're supposed to subtract it.
That's why I put them together with a single little wire going into the new loop there of 2 resistances. Right, 8.06 milliamps. We worked that out here, 8.06. So let's just slide him back over again. And
He's lost me again, man.
I've lost you again. All right, let's keep up with this. 307 divide by 560 times 8.06 equals 4.12. 4.42. Okay, they add up to 8.06. So 3.64 through the 680. If this is 680 and this is 560, how small can we write? Oh dear. Red text to colour. 680 gets 3.64. 560 gets 4.42. Milliamps. You see, that's my second current divider. The current comes, how about I redraw this here a little bit? How about I rub that wire out there?
So the current divider we can use it only when we have 2 resistors, right?
Hang on. There we go. Let's rub that out and do that. So that 14.42 has split. We did the sums for it down here to give me 6.34 milliamps going down there and 8.06 going that way.
So you gotta make that clear that it splits and then 2 different currents.
And then when the 8.06 comes in here, guess what? It splits again. It's another current divider. 8.06 is at, oh, where is that? If anybody goes to Officeworks, if you buy me an orange whiteboard marker, I'll pay you for it. I'll try and get there and I'll try and buy some different colours. I've seen purple ones, you can get purple ones and orange ones, and they work really well with video. But green and blue, they don't really work too well. So this again, this corner here, I redrew down here. Here's the 14.42 coming in, 8.06 comes into these 2 resistors, then it splits to make 3.64 in that, 4.42 in that. I did the maths here. 3.64 I worked out by the REQ of that divided by the 680 ohm times the node current which is coming in, which is 8.06, and that's what we've got there. 8.06 plus 6.34 added back up to give me the 14.42 that had split originally. We get a split, then we get another split. You can have many splits, multiple splits, big circuit, lots of resistors, lots of splits. You see? And the 4.42 was on the 560 side. 560 was the bottom resistor. You add the 4.42, 3.64, they add up to be 8.06. So now we actually have every single current solved in the circuit. I can tell you exactly what current is going through what resistor.
How can you just change the circuit though for R2 and R3? When on the original drawing it shows it coming in from the top and then it goes across.
And then
down.
from here. But hang on, that's a piece of wire coming down there. Wire is a short circuit. So the only difference, if that one there came over there originally, what's the difference with me just going through that bit of wire and joining up? They're all joined.
It wouldn't like conventional flow would go sort of across and go like that?
No, it's a piece of wire. Wire's got no resistance. The wire's a short circuit to the current. So it makes no difference if that one's drawn across there and then if I've just rubbed that out and moved it up there. On your breadboard this afternoon, when you wire this up, you should get a better idea of that, because on the breadboard, it's up to you where you plug the resistor in, just providing that R6 meets up with the top of R2 and the top of R3 and the bottom of R1.
Right.
Yeah, it's just a different way of drawing it, and you've got to get around that. That just comes from practice. Abstract. Circuits are very abstract, and I guess I'm probably a little bit good at art, so when I was about that big, I got pretty good at circuits and schematics, yeah. I was probably a bit gifted in that way. What else did we have to do with this? It said solve all the currents, voltages, resistance loops. We've done the loops. How's our camera going? Is it all good? Yeah. Camera's all good. We've done the loops. We haven't worked out the voltages. We've done the loops, we've done the currents, we haven't got the voltages. How do you work out voltages?
Yeah, simple.
V equals IR.
Yeah.
So, if we know the current going through that, can we work out the voltage across it? Yes, we can. 14.42 times 270. 0.01442. 42 times 270 equals nothing. 0.01442 times 270 equals 3.9 volts. So the voltage across that resistor is 3.9 volts. What about this resistor down here?
Same.
Why is it the same?
So that's a series circuit.
It's series, so
The voltage is same.
hang on, the voltage isn't the same. 270 ohm, 330 ohm. How do I work out the voltage across that?
Same method, just times it.
Times it by what?
Times by what? By the current.
Which is?
0.144 amps. 0.0144 amps.
14.42 milliamps. Why is there 14.42 milliamps there? What goes in has to come out. I love it. What goes in has to come out. So we had a node there. We've got another node there. And after this current splits and some goes down there and some goes there, some goes there, combines again, comes down there, it all comes back out. You're absolutely correct. 14.42 milliamps. 14.42 milliamps. And then how much does that give us in voltage there? Did you work it out?
No, I can do it now.
0.01442 times 330.
4.75 volts.
4.75 volts, maybe even 4.76. 4.76 volts. And that is across that resistor. So, in other words, and this is, look, I'm going to do this. I'm going to get the multimeter and do it. I've done this before because I think a lot of you are going to need practice at this. When you measure voltage, turn the multimeter on, make sure that you've got the probes in the right holes, common and volts, ohms, DC voltage, choose the range. It's a manually ranging meter, so start on the 20 volt range. You can always go lower afterwards. If you want to measure the voltage across the resistor, think about it, leads, you're measuring across the resistor. You're putting the meter across the resistor, and that will measure, if everything works out for us, 4.76 volts. And if we go across that resistor, we'll measure 3.9 volts. How do we measure current? How would I measure current using this meter?
By flicking it to the current.
Okay, so let's do that. I'll run with you. So you don't flick it to the current range before you do something else. You've got to move the lead, the red lead from volts ohms, and we'll go into the milliamps socket. Milliamps, common, then we flick it, and we have to choose the DC milliamp range, and I'll go to the 200 milliamp range. Always start on the highest range. How do I measure this 14.42 milliamps? I can't put the meter across it. Measuring across the resistor to measure the voltage was easy.
You can do the other side of the battery?
I can't put this across the wire to measure the current
Doesn't it
because
have
the
to be
wire is a short circuit. I don't dare put that across the battery because I'll blow the fuse in the meter up.
Doesn't that have to be part of the circuit?
It does. Can you explain that more?
Or you take out a bit of the cable and then you
Take out a bit of the cable? Oh, Matthew, what did you have for lunch? You're doing really well. I have to take out a bit of the cable and I have to put the most positive side of the milliammeter to the most positive side of the circuit, positive, there, and the negative side there. Do you remember back in week 2 we learned about meters? Current meters have very low internal resistance, so they don't interfere with the circuit. So therefore, that goes in there. Now, all the current that comes along goes down the red lead into the meter measures the current, and the current comes out the black lead, and the circuit is unchanged. So to measure current, we have to do what Matthew said. We have to break the circuit. Break the circuit. That was a pretty big circuit to solve, wasn't it?
To cut off the wire.
In the breadboard, we'll find that we just unplug the wire. Now, I'm going to teach you this afternoon about how to use these breadboards. And in the breadboard, we'll simply lift a wire link up, and then we'll be able to do our measurement, and then put the wire link back in again afterwards. Yes.
So did you work out V2 and V3's voltage dropping already?
Haven't yet. I did the common ones at the front. V2 and V3.
That's the
VR2 and VR3?
yeah.
We can do that. How much current's going through R2?
How much current's going through R2? It's 8.06 milliamps.
No.
Hell no, you said
8.06 is where my finger is. Right here where my little pinky is.
3.64 milliamps.
I got 8.06 there and I got 8.06 there.
It's 3.64.
Oh, so it splits.
Down here. 680, 3.6. We did the sums on the other side of the board, remember? 680, 560, current divider rule, 3.6, 4.42. 4.42, don't have to think too hard about it. Higher current, smaller resistor. 560 ohm has 4.42, 680 has 3.64. 3.64 milliamps times 680 will give me the voltage.
Oh, I did do that.
3.64 milliamps, 0.00364 times 680. 2.47 volts. Need more Wheaties. 2.47 volts.
2.47. Do you use just basic Ohm's law there?
Absolutely. And you'll find if you get the current going through the 560 and you multiply it by the 560, you'll also get 2.47 because they're in parallel. So let's do that. The current through the 560 is 4.42 milliamps. We get the 4.42, we multiply it by the 560 because V equals IR, and we'll also get 2.47. So 4.42.00442 times 560. 2.47 volts. Parallel resistors, same voltage across each resistor. Isn't that amazing? Enough? Are you saturated? The camera just turned off just then? Alright, that'll do.
You had me up to
Maybe I'll just...
R4 and R5, so the voltage over there.
I'll do those. Okay, so we've nearly had enough then. We've got the voltage across those, the parallel combination. R4, R5, they've each got 8.06 milliamps going through. 8.06 times 330 ohms. V equals IR again, and the same current, 8.06 times 150 ohms.
Same Ohm's law.
Same. And the current going through that one there worked out to be 6.34 milliamps going down through R6. 6.34 milliamps times 1K, 6.34 volts. 6.34 volts plus 4.76 volts plus 3.9 volts, guess what? Adds up 15 volts. You can do all the checks on it. It all tallies up. It's just like when you get a good accountant, he can make your piggy bank balance. All good?
Yeah.
Well, I know you're not, but if you sort of feel that you're sort of understanding it,
You get the idea.
good. You got the idea. Okay, you've got the idea. You can see there's a fair bit of work. Yeah. And I've said previous weeks, look, it's not rocket science, but it's also not super easy. There's a fair bit to take on board, a lot of fundamentals to take on board to use to be able to do this. All right. I do it easy because I've done it lots of times. When you're learning, this is pretty hard stuff. No one's going to tell you it's easy. Okay? We'll do a lab then now.